So you found the skeleton. How would you tell people that you personally? How would you decide?
Well, interesting question. I don't know. I'd have to do some research on that.
Hello everybody, the Dapper Dinosaur here with, of course, Sal Cordova. Let's make Sal a little bit bigger just for now. We'll get rid of this slideshow. We are here to talk about the second law of thermodynamics. Sal is, in fact, a young Earth creationist, but unlike many of them, Sal is going to argue that the second law of thermodynamics is not a good argument for creationism. So, Sal, why don't you let everyone know a little bit about yourself and say hi, and we'll jump into your slideshow.
Yes, I'm Salvador Cordova. I run the Evidence and Reasons for the Christian Faith video channel, and it's an honor to be here. Dapper Dino and I have debated each other once on Modern Day Debate. It was a very friendly discussion, and
yes,
we ended up liking to hang out with each other. It may seem funny that I build friendships with people who don't share my views, but that's, as opposed to other creationist channels, I don't have a policy just trying to keep channels of communication open. That's partly because I've matriculated through secular schools, and I've had professors who have taught me and mentored me who didn't share my creationist views. So it's not unusual for me to be friendly to people I perceive that have very scholarly interests, like Dapper Dino. And he's been on my channel to talk about like the early Christian church fathers, and that was one of my favorite shows on my channel. And I said, I'll horse trade with you. I'll do a talk on thermodynamics on your channel. So professionally, I was a scientist and engineer in the aerospace and defense industry. And then about 7 years ago, I started working for Dr. John Sanford, who's a relatively well-known young Earth creationist in the creationist circles. I was a molecular biophysics research assistant there. So that's a little bit of my background, and I'm going to be talking about why the second law of thermodynamics, particularly the concept of entropy, really more the concept of entropy, is actually pretty bad argument for biological creation.
Okay. Well, that's awesome. So let's bring back your slideshow, and let's have you dive in, because, I mean, for the most part, Sal here is going to be running the show, because he is the one who wants to correct people on his side about thermodynamics. So he's going to mostly be running it, and if people have questions or anything, you can put them in the chat. The only ones I guarantee that we'll read are the super chatted ones, because I can't guarantee we'll see all the questions, and also some of them might not feel like they're relevant by the time I get to them, so that might be a thing. But and of course, if I have questions, I'll stop Sal, because I have the power of the mute button, which I don't actually expect to use.
Right. I have to transmit some links to my other computer, because it's in the other computer I can dump links in the chat. And so if you'll permit me just a moment, I'm going to do that before I get to my slideshow. So if you have any announcements for your channel or upcoming shows, it'd probably be a good time
Let's
to do
see.
that.
Upcoming shows. So my schedule for this week is pretty normal, but the Saturday after next, I'm going to be doing a Leaving Young Earth Creationism with someone named Kat, and so that will be on the 7th, I believe. And then I actually have another Leaving Young Earth Creation set up with Jordan from Reason to Doubt, or Reasons to Doubt. I don't remember which one. But yeah, so he's going to be coming on. He's actually going to be on a Tuesday because he couldn't make it for one of my normal Saturday slots. So actually a month from today, which will be on a Tuesday, I'm going to be having Jordan on for Leaving Young Earth Creationism. So we got 2 of those scheduled in the next month. That'll be nice, because it's been a while since we did one of those. Also, if you want to see my most recent thing, it wasn't actually my stream it wasn't actually my stream on David Neff's channel yesterday. I then very quickly went on and went on to Smoky Saint's channel, of all things. Yep. I went on, it's my first and so far only time on Smoky Saint's channel. but we went on to talk about the age of the Earth. And so, yep, it was, it actually was a friendly discussion. And so, Smokey Saint, on the off chance you're watching, thank you for having a nice friendly discussion with me. I can't say that I've always expected that to be my experience if I went on your channel. However, it was this time, so I say keep it up, man.
Well, awesome. So this was a picture of me at my first debate, modern day debate, and you see Erica there. And this is just, this looks like such a happy family. And I'd like to think of kind of the gang at our YouTube friends as a happy family. And there was me with Dr. Dan in debate with Erica as moderator. And James pulled a little prank on her because that was the weekend. That was the day, July 1st last year, she announced her engagement. And that's not her fiance. That was
Erica
just a prank.
can be the fifth ex-Mrs. Hovind.
So I put a link in the chat in case anyone's interested. My life story was actually in the cover story of Nature, April 27th, 28th, 2005. I put a link in the chat just in case you're interested, my involvement in intelligent design. And so today I'm critiquing some things. James Tour had a series on abiogenesis, and for the most part, I agreed with it, but I took actually some exception to comments by Brian Miller, who was there. And Brian Miller and I are on good terms. We've corresponded. He's with the Discovery Institute, and I'm going to point out some problems with using the second law of thermodynamics. Fundamentally, and the concept of entropy, fundamentally, it's just too clunky as a measure of disorganization or organization.
Okay. Can we, before we really get in there, can we get through the laws of thermodynamics? So I'm not sure everyone knows what they are. We throw these terms around, but can we start with, you want to start with 0 or you want to start with 1?
Actually, I'm going to go backward if that's okay.
Oh, hey, that's fine too.
I'm going to go right for the jugular and say, okay, if you're trying to argue with a creationist, so let's say just a little bit more friendly, we'll say creationist versus other creationist. All right. So it could be someone who's evolutionist or atheist or whatever versus creationist, but let's say just creationist versus creationist. So if I were arguing and saying, hey, don't use this second law of thermodynamics to argue that God created life, this is how I would do it. The first thing I would ask is, I said, can you tell me what has, I just took a book cover because I'm going to talk about mice and men. Can you tell me what has more entropy, a frozen dead mouse or a warm living adult human?
I mean, I know the answer.
Yes, why don't you tell us what has more entropy?
By far, it's the living warm human.
Yes, absolutely. And I'm just like, okay, you keep talking about reducing. The creationist says, well, entropy keeps increasing. You have to keep reducing it so you can have life. I mean, that's kind of the general notion. And that's exactly the problem. When you actually subject the analysis, subject the organisms or the objects to thermodynamic analysis in terms of the differences in entropy, it doesn't work.
Yeah.
So that's it right there. Just that's it. That's the jugular argument. Confront the creationist who's using this stuff and say, can you tell me what the change in entropy is from the dead or living state? Or make it easier. Can you tell me what has more entropy or less entropy? The frozen dead mouse or the warm living adult human? And so that's it. You'll start to, if you're in a debate, just throw that out there. And I actually did that to someone who was an ID proponent, Granville Sewell, who was making a big deal about the second law of thermodynamics, showing that the complexity of life could not arise naturally. And I said, Dr. Sewell, I'm sorry to be anal about this. And, I tried to be gentle at first, but then I had to just kind of take a stand. I said, can you give me a calculation of the delta S being entropy? So we usually use the word just delta S. Do a calculation from when a cow is alive, and then you take a bullet and take a gun and kill it, or however you execute him.
Right.
Do a calculation of delta S. He said, I can't.
Well,
And I said, that's
you can't make that argument then. We have a question for 50 Danish kroner, I believe. I think I got that. Look, there's so many different like currencies out there. I'm usually guessing. So I'm pretty sure this is 50 Danish kroner from Danish Debater, who says, Sal, if you had to recommend one science book for and one against your position in general, what would they be? Also, will you and Dan talk again?
I hope Dan and I will talk again, and I'm looking at my second computer here, and very nice to see you, Danish Debater. Nice to see you again. Thank you for your contribution. If I had to recommend one science book for my position, for intelligent design, it would be Stairway to Life by Dr. Changetan and Dr. Rob Stadler. Dr. Changetan and Stadler are Harvard-trained scientists. And so they're real scientists, unlike the guy who runs Dinosaur Adventureland.
Ooh, burn.
Yeah. I'm going to get flack from that for saying that from my fellow creationists. But you know what, guys, at some point you just have to stand on principle and say this the way he's treating, I'm sorry, I just have to be, excuse me, but I just have to, I have to take a stand and try to defend good people out there and just steer them clear of charlatans. I'm sorry to have to say that. I'm going to take flack for saying that, but you want good creationism, and thank you for Danish Debater. For intelligent design, it would be Change Loratan and Rob Stadler's Stairway to Life. You'll get a headache reading it because it's very technical. It's written by university professors at secular universities, Changetan Secular University. For creation science, young earth creationism, I'd say it's a free online book, creationscience.com. Walter Brown's In the Beginning, but he put the book for free online.
That's
so
awesome.
I'd say now I actually don't know what the best single book is against my position. I think that you'll probably hear a lot of good material on Dapper's channel of what books to recommend. I'm not very much into the geology aspects, and I myself will actually critique some of the young earth creationist arguments and say, either that's not very good or it's unproven. I don't spend a lot of time doing that. It's hard enough to try to prove your case, and then to critique other parts of it, I just leave that to other people. So I'm sorry I can't answer the question, what would be the one good resource? I actually do read a lot of peer-reviewed biology literature.
But it's hard to recommend that, right?
I mean,
the
it's
same
just
thing.
piles of obscure stuff. It's not popular reading. Most of my reading of evolutionary biology is not popular level reading.
When people say, hey, what should I read to learn more about dinosaurs? I'm like, I don't know. I'm just reading papers, but I don't recommend that unless you're really into this. But I haven't been keeping up on popular level literature on dinosaurs because it no longer interests me that much, because at this point I'm like, I need to actually get to the papers, because the popular level stuff is usually dragging behind 10, 15 years or so in a lot of cases. And so I'm just reading papers, so I have no idea what to recommend for people when they say, hey, what's a good lay level dinosaur book? I'm like, I don't know.
I actually like Richard Dawkins' The Blind Watchmaker. Now, I totally disagree with a lot of it, but his English is just fabulous. I mean, if I could write like that, that would be awesome.
It's funny.
That's one of my favorite, honestly. I
really like a lot of his biology books, and I hate his philosophy books.
Yeah. So I like The Blind Watchmaker as a young earth creationist, but again, it's a little bit obsolete, but that was really my favorite of the other side. So
maybe that one can be your recommendation, though, The Blind Watchmaker. I mean, it's a little out of date, but it's not like it's completely outside the pale of just completely been passed by biology. There's still a lot of stuff in there that's still reasonably in line with current thought in scientific literature. But let's get back to the second law.
Okay, so I'm just going to show some calculations how this is, how you can make that argument. So I think you'll just stop the creationist in his tracks if he tries to argue second law of thermodynamics precludes the evolution of life. And it was an unpleasant interchange because I really like Granville Sewell, but I said, I had to point out to him, you're not going to make a good case if you can't even do a sample calculation to say that entropy is either increasing or decreasing. I said, you have to show it. And I actually did examples where you take a 747 and you rip it to shreds, and you can argue, depending on how you define the remainder of your scrap pile after it's gotten kind of disassembled, like say a wing's torn off, it actually has lower entropy after you tear off its wings. So
yeah, all things being equal, if you just lower the amount of stuff in a system, it's going to likely end up with less entropy. So
yeah. So exactly what you just said. If you could repeat that.
Oh, so I said,
the
all things being equal, if you just remove the amount of total stuff in a system, that system will end up with less entropy.
Exactly. Because entropy is what they call an extensive property. The more stuff of it you have, the higher it is. So
Right.
Just like, yeah. And we'll go through, I'm just going to go through an example here. If you go to the Wikipedia water page. Now, what I'm going to say here is, when I was studying entropy, the professor gave me the same answer that I just gave Dapper Dino when he asked, can you go over the definitions? He said, well, if you want to understand entropy, just calculate it. Don't ask what it is. And so this was what was kind of funny. At the end of our class in Statistical Mechanics and Thermodynamics, graduate level, he said, I don't really understand entropy. I don't really understand entropy. I knew what he meant, and I'll explain why he said that. So this might seem strange that I'm going to go to actually calculating it first and then trying to explain what it is later. So let's just go to if you go to the water data page on Wikipedia, you'll see this thing called the standard molar entropy right there in water in the liquid state. So, I'm just showing for reference, and I'll show how it's used. And then you have water in the solid state, the standard molar entropy. And then you can do a calculation. What's the change of entropy when you take water in the standard liquid state and then freeze it and take it to the standard solid state? You end up reducing entropy just by cooling it off.
Yeah.
So the idea is that with a frozen dead mouse, or let's say you had a warm living mouse and then you froze him real cold, you've actually lowered his entropy, you've killed him. So lowering entropy doesn't necessarily mean you're going to make it more complex or functional or whatever.
And it's one of those things where creationists like to conflate the idea of orderliness with entropy, and it's just like, you can't do that. This is a physical property of systems that has to be calculated, and it does not correlate well with how orderly humans are going to pretend the system is.
Exactly. So, and you can see here, 1 mole of water is roughly 18 grams of water, or 18 milliliters of water, which is about the volume of, say, 2 ice cubes. So you could see then that the more water you have, the more entropy you're going to have.
Yeah.
Just as the more stuff, just like what we said earlier, kind of a rule of thumb. It's not rigorous, okay?
Right.
So the more stuff you have, the more entropy. So the more water you have in the system, the more entropy it has. And so if I'm not monitoring the chat, if you see something where someone seems confused.
Well, there is a question. Sal, this is from Nestle20. Are you familiar with Sharon Glotzer's work showing that the process of increasing entropy can increase order?
No, I'm not. Not at all. I didn't know that. So thank you.
Nestle, if you want to shoot me a message on Twitter or something with a link that I can pass on to Sal, I will make sure to do that.
So what was the comment again?
It was
showing that the process of increasing entropy can increase order.
Yes.
Yes, I have an example of that, by the way. So I saved one, but thank you for mentioning that. I think I've seen Nestle also make some other comments on your channel that I was very impressed with. So just wanted to salute you.
Nestle is Nestle 20 is a smart guy. That's why I let
Oh,
him
yeah.
on sometimes.
Oh yeah, he. I saw one comment on single-stranded DNA and heating or something. I was very impressed. So just wanted to say, Nestle, when you say something, I try to pay attention. So I think that's straightforward. So all you have to do then is, let me see if I actually did this. Yeah, so you just go through the calculations. You can calculate then the difference in entropy between mice and men. This was from a prior presentation where I actually walked through this. So I mean, I'm not gonna go through all the mechanics of it because I think we've already made our point. So the remainder of the show is just more or less just kind of fleshing this out, because at that point, I try to have simple arguments. So I'm just going to move forward and just kind of just flesh everything we set out to try to help understand entropy. So in my class, the idea was calculate entropy first, then you'll understand it. Normally, you try to define the term first before you calculate it. Entropy is so complicated sometimes, and there's so many pitfalls and differing conflict, almost not quite conflicting, but not identical definitions even of things like temperature and microstates that are different depending on the literature and the era that you're referencing. It becomes a real mess. So I just wanted to encapsulate everything we really needed, and it's basically boils down to just this simple question. Just throw that on the table, and I think you'll win the argument. I've not heard a creationist refute that problem adequately, and I'm saying, why do you want to even use that as a measure of organization or order, or disorder or disorganization? It's just too much of a mess. So don't use it if you're a creationist. So I cringe when I hear creationists throw this in a debate, and it's like, you're going to lose. If someone is smart enough to throw this out there, they'll have you.
That's why my first question to creationists who throw this out there is, okay, what units do we use to measure entropy? And the thing is, you're the first person that I've known who's a creationist who got it right, which is one of the reasons why I started talking to you about this subject. Because everyone who uses this can't even give me, oh, it's joules per Kelvin. Like, none of them know that. And it's just like, guys, if you don't know what the unit is for entropy, maybe don't use it as an argument.
Exactly. So in the time remaining, I've given you the best argument, the easiest stuff, the best stuff first. The rest is just going to be boring mechanics, and we'll just walk through it until we're tired and we run out of time. If that's okay, Dapper.
Oh, that's fine by me. Yeah.
So Brian Miller, and you'll hear a lot of information theory guys. So my another big pet peeve, please don't use information theory to argue.
Yes.
So
there's another thing I never get units from young Earth creationists.
I just, and I'll throw this, I've gotten flack because I've sometimes criticized John Maddox, and Standing for Truth said, pay attention to what he's saying. I'm just like, dude, I probably have more information theory background than anyone here. Don't tell me that. I was really offended.
What, SFT being mean and offensive? No, that's impossible.
But one of my undergraduate degrees was in electrical engineering, and I did take graduate level information theory. And I just tell the guys, don't use it. There was a big move in the about 20 years ago for specified complexity and complex specified information. William Dembski was the proponent of it. I consider him still my friend. He was my mentor. He invited me to be his graduate student at Baylor with Robert Marks in 2007. I ended up going to Johns Hopkins University instead of going to the evolution informatics lab. And it may be just as well because I concluded a lot of his math work for ID was just not very helpful. And so the infusion of information theory into the ID argument, I felt, made it actually worse, because I like simple, clear arguments. And this is like one of my information theory books here, Principles of Communication. And I actually am working and have, I have a peer-reviewed press release I talked about on my channel. We actually did use information theory to do some structural biology and proteins. But that's like the one time I'll say, use information theory there, but otherwise just don't do it. And then Brian Miller will then start combining information theory with second law of thermodynamics. It's like, boy, talk about two bad things you don't want to do. So I'm going to get flack for this. So for the creationists want to hear how I argue it, I'd say just change Tan in Rob Stadler's book, Stairway to Life. That's how I argue intelligent design. I don't use information theory. So I'm just going to read my PowerPoint notes here. If you'll forgive me. I'm not,
No, I'm actually going to make them bigger.
Some people are very good extemporaneous speakers. I am not one of them. So a warm living human has way more thermodynamic entropy than a frozen dead mouse, based on standard molar entropies of water alone, and the fact that thermodynamic entropy is proportional to the number of moles. Gilbert N. Lewis of Lewis structure fame, so those who study Lewis structures in chemistry, said, gain in entropy always means loss of information and nothing more. So for the sake of this presentation, let us call this the Lewis principle of thermodynamic entropy in information. So if a warm living human has supposedly more thermodynamic entropy than a frozen dead mouse, then conversely, a frozen dead mouse has more thermodynamic information than a warm living human. Does that sound absurd?
Yeah.
I'll say yes.
Yeah.
This apparent absurdity results from the conflated and equivocated meanings of information. The idea of loss and gain of information in thermodynamics can be the exact opposite of what we mean as gain and loss of information in the conventional sense. End of rant. So I'm just saying, including information, second law of thermodynamics and information theory in a critique of abiogenesis research, it's like walking a minefield of unnecessary confusion. And so in James Tour's talk on abiogenesis, I liked most of it, but when he started referencing Brian Miller, I said that this is not helping. It's just throwing confusion factors. It's like trying to kill a fly with a sledgehammer. And there's actually a picture of, I borrowed whoever photographed this picture. Thank you. Because it conveys my feelings about trying to do this. And just imagine a fly on your head and you're trying to swat it with a sledgehammer. Don't do that. And so I went, this is again, just, I said that a frozen dead mouse has over 1,000 times more thermodynamic information than a warm living human. And again, it depends on how you define information.
Right.
And
if we're just going to define it as entropy, well then, there's a lack of entropy.
Yeah. And it's like, okay, what do you mean by information? I'll give you another example. Let's say you have a 1 megabyte MP3 file. How many bits of information are in it? Because you decompress it, it's going to be like 30 times bigger, and you're going to have a debate. And I said, well, it depends on what you mean. And that's not
actually
that's exactly why I don't use information arguments. It depends on what you mean.
That reminds me of an example I gave in a video I did once, and it was talking about information theory. And I was like, the problem is that it's hard to define information, and no information theory defines information in a way that's intuitive to humans. And as an example, I had a black and white grid that I saved as a JPEG file. The JPEG file was extremely small, right? It's just a black and white grid. But then I had saved a different JPEG file of the same resolution, but it was actually just completely random noise that I had generated, with a filter on an image editor. And it was a much, much bigger file. even though for most people that grid seems more orderly and has more information, you could play a game of checkers on it or something, and the noise is just literal nonsense.
Right.
It still requires more information to store it. So our definitions of information, when we're actually talking about scientific fields, does not correlate well to this intuitive notion that a lot of young Earth creationists like to say was like, oh, you can just look at it and tell it has more information because it's bigger and better and stronger. It's like, nope, that doesn't work.
Yeah, and also the ID proponents. So yeah, I'm not, I get a lot of flack because sometimes I'll just put my foot down and say, no, this guys, just because you're on my side doesn't mean I'm going to agree with everything you have to say. And so now we get to the question, what is entropy? And I just say, ugh.
Yeah. I have a few okay definitions, but
Okay,
yeah.
so I'm going to try to just say why. I'm going to go back and you can actually put my face back
Yep.
on the screen because I feel like, I don't know, that's just kind of a little preference, but I just, going back to what my professor said, he said at the end of our Statistical Mechanics and Thermodynamics class, and it was a hard class, our textbook was Patria and Beale. Just, I mean, you can look it up. You could see it's pretty thick. And he said, I don't understand what entropy is. And I know that was really a figure of speech because clearly he understood in the mathematical abstract sense.
Mm-hmm.
But let me explain what he means by that. So depending on how, I'm going to leave this question to the philosophers of physics. But what are the fundamental units? Sometimes you'll get, how many fundamental units are there in physics? And sometimes you'll get the number 4, sometimes 7. Okay, I'm not going to be anal.
Yeah,
I like the number.
I might add spin.
Okay.
Like because there's that quantum mechanical spin that isn't any of those 4 things, and it's also not a physical rotation in space. So it seems fundamental. I might add spin in.
Okay. So yeah, we're not going to be anal, but I'll just, we can build a lot from these fundamental units. So whether it's 4 or 7. So in one physics textbook, it listed as 4.
Yeah.
And usually when I think of things, it's like, okay, most of your physical quantities are length, time, mass, and charge, electrical charge. So you have an easy concept of what length is. So you can compare, like, this is longer than something else. Easy. Same with time. 1 year is a lot longer than 1 second.
Right.
You have a sense of what these quantities are. Same for mass. Something's heavier than something else. Charge. Yeah, you can. Like a lightning bolt has a lot more charge in it than say a battery. So they're intuitive things. And then if we go to the SI, I just took this from the National Institutes of Standards, and they give what they consider the fundamental units. It includes the 4, so to speak. Amperes can be said the amount of charge per unit time crossing, flowing across a cross section, something like that.
Almost. Charge doesn't flow, but it's a little,
Okay, thank you.
Yeah,
thank you.
That's I was an electrician for a while, so every once in a while my electrician training comes out and I'm like, oh, actually, jungle jargon.
Yeah.
He apparently thinks that batteries are just buckets that you pour electrons into. I tried to correct him on this. Also, for $4.99 US from Vandalia 1998, we have just saw Niagara Falls with the nieces. You two talking about that this debate. Didn't see any barrel attempts. Well, sorry you didn't see any barrel attempts, but this is not a debate. This is actually a friendly conversation where Sal and I are on the same side, which I think is at least as much fun as when we did debate, because it was an extremely cordial and friendly debate.
So what is a barrel attempt?
That's when you try to go over the Niagara Falls in a barrel and also not die.
Oh, okay. So, again, you can look at this, and this is funny. I actually never worked with luminous intensity very much. I mean, I might know it from another, there's might be physical concepts, but I had it in my own language. So
I did a bit of that when I took an astronomy class in college as an elective. A lot of
okay.
luminosity.
All right. Yeah, my astrophysics teacher, he was, oh my goodness, he was just really into the math. I'm just like, okay, this was a nice math class, but I don't think I really learned any astrophysics or astronomy. Everyone kind of said, yeah, he's a physicist, but he's a closet mathematician because that's all he thinks about is math and teaches. Anyway, so again, we have length, we have time. You can say amount of substance, you're just kind of counting. Electric current, which is
it's the amount of electrical energy crossing a certain section of conductor per unit time.
So the way we can count electric charge is in coulombs. And so when we say coulombs per second, that's the amperes. And then temperature. Now this is interesting. When we use the number, if we use just 4 fundamental units, it's like, where's temperature? And so this leads to I'm going to cover this kind of the historic issues with temperature, because there are 2 definitions of temperature. You can use them not quite interchangeably, but for practical purposes, you could say they're the same thing, but they're actually defined differently. And I'm going to cover that. So you can either make temperature a primitive unit, or with a great deal of difficulty, you can relate it in terms of length, time, and mass. That'll seem strange, and I'll cover that a little bit. So what does this have to do with entropy? You see, so much of what you see, at least in the list with 4, you can conceptualize it. Human experience describes it. You can describe it in terms of your human experience, what length, time, mass, and charge are. The problem is now, what do you do with entropy? You can also get a sense of what temperature is. You sense cold and hot. But how do you what is in our human experience that gives us a feel for what entropy is?
It's basically nothing.
Yeah. It's an abstraction, and that's what I believe my professor was saying. He said, I don't understand entropy. He understood it in the mathematical abstract sense, and in a way, that's the only way you understand it as a mathematical abstraction, because he said you have to calculate it to understand it. You don't experience it like these other fundamental units. And so that's the problem of defining it. So by the way, so we can take like the units, like kilogram here. Let me see if I can. So kilogram here is a measure of mass. M, unfortunately, it means meter. Sometimes M means mass. It's just confusing. So kilogram is measure of mass, meter is a measure of length, and seconds is a measure of time. And so the famous unit, the Newton, is kilogram meters per second squared. And then a joule is newtons, which is this, times a meter, and a watt is joules per second. So we can build all these other units from those 4 fundamental units.
Right.
The tricky part is when you get to temperature. And then there's also kind of 2 ways to compute entropy. The Clausius way, you normally compute only changes in entropy, what we call delta S. Now, if you combine that with what they call Nernst's theorem, the 3rd law of thermodynamics, sometimes you can say, okay, we could say you can calculate it from the state of 0 entropy, and then you can kind of calculate an absolute entropy. I don't, in any of my homework assignments, we never went there. Okay. But suffice to say, Clausius had kind of the more, he was the first one to kind of define the idea of entropy in this way. There might have been some others that had, but he's the one that, we talk about the Clausius integral and stuff. This is the way he defined it. the reason this is good is you could actually use calorimeters and thermometers. If you can use calorimeters and thermometers, so the calorimeter will tell you how much heat is going in or out of the system, and then you have a thermometer to tell you the change. So you can actually you can it's funny, you can kind of say, okay, this much heat, I get that, and then you have temperature, then you can calculate the entropy. Boltzmann, now interesting historical point, this was before we had any theory of atoms. This one had no theory of atoms. In fact, he actually had a theory of heat called the calorie theory of heat, that heat was actually a physical substance that would flow in and out. Now it's more subtle. Heat is, I'm going to get myself in trouble here, but we have an idea of what we call internal energy. Like, say, if you have a container of gas, the internal energy is like the entire kinetic energy of all the molecules bumping around. And so when you have heat exchange, you're exchanging the kinetic energy in one system to another, and the amount of kinetic energy exchange is the heat. So heat's kind of a funny thing. I probably didn't get that 100% right, but there's some subtleties there. And for the people that are really persnickety about that, feel free to correct me. But
with this audience, don't worry, they'll correct you in a dime if they think you got something wrong.
So I want to point out something here. Entropy here is very critically dependent on a primitive notion of temperature. Boltzmann's definition of entropy is critically dependent on this notion of microstates. So we can do a logarithm here, and actually you don't need K. If you have natural units for entropy, you actually only need this omega or W. W is a nice English approximation for the Greek letter omega. So this was on Boltzmann's grave. And actually, it's funny, the exact formulation, this equation was by Planck. So Planck took Boltzmann's work and represented it this way. So the equation, I also want to give credit where credit is due. It's Planck who stated it succinctly this way, but it's Boltzmann who came up with a lot of the ideas. So Boltzmann and Maxwell and Gibbs were some of the pioneers of atomic theory. And they were actually the rebels because especially Boltzmann got attacked a lot for his views that atoms are the correct description of matter. The persecution he suffered may have led to his suicide, which is just a real tragedy.
That is too bad. We have a quick question. So we affiliates would like to know, what is the Q in the Clausius equation? Heat.
So that's the change in heat.
Yep.
So there's some real nice ways this can be done. Like you can get a nice approximation, like when you're changing from the ice state to liquid, and you just, because it happens at the same temperature, all you have to do is just use your calorimetry and determine how many joules. And because the temperature is constant, it's a very easy integral to execute. And I've actually seen that in chemistry exams. Calculate the change of entropy, and they'll give you one of those really easy integrals to solve.
Now, that T, that's time, right?
Temperature. Temperature. Yes, it is temperature.
We're having some pushback in the chat. There's a little debate on whether that's time or temperature. Uh-oh.
It's temperature. It's temperature. Yeah.
So the reason I would think it might be temperature is because if you're already taking the first derivative of Q, you're already including time because you can't take a derivative of a single point. You have to take a derivative of a series of measurements.
Okay, so let me just try to say this. Let's say the ice cube melts slowly or quickly. The amount of time it takes is not relevant. It's this, you're going from one state to another, from the solid to the liquid state. And the change of entropy is what they call a state function. It's like temperature. It's what's the state of the system. And so when you've gone from the liquid or solid state to the liquid state, no matter how long it took, like, if that ice cube were, let's say in an insulated container versus the ice cube on a hot day, during that state transition from the solid to the liquid state, while the temperature is still the same, because while it's melting, it's still at the melting point is melting temperature is maintained.
And guys, I'm double checking on Wikipedia, and they are confirming it's temperature.
Temperature.
Plus, big T is usually temperature, small t is usually time in scientific equations. So.
No, but thank you guys for double checking. I'm not going to get everything right. I think I'm close enough. Okay, so the point is that you could see heat, the change in heat, and then temperature is very important. In Boltzmann's definition, you just have this omega term, and omega is a mess. So a lot of times it's nicer to use Clausius because it's easier to conceive, but then you begin to wonder what does temperature mean? And then where this is important, and this is where Nobel Prize winner Linus Pauling made a great contribution, you can use calorimeters and thermometers to measure changes in entropy. Boltzmann helps you describe this at the molecular level, what entropy is. So you can actually use your calorimeters and your thermometers to determine, like, say, what's going on with the molecular structure of ice. And that was a very famous paper. He was relating molecular structure of ice and confirming it with calorimeters and thermometers, which is amazing. So if you want to, he's trying to estimate, because you really don't have microscopes that could see at that level, so to speak, especially in that time. He could see that he can conceive in his mind the molecular structure and whether it was consistent with our measurements of entropy. So both definitions are really important. We normally don't have a way of measuring microstates, this W, this omega, directly. So what we'll do is we'll make measurements using the Clausius integral, and then we can use that to maybe inform what we think the molecular structure is. If our model of the molecular structure is accurate, it should give predictions on what this delta S is. So that's okay. So depending on which school of thought you're coming from, and you try to use both, actually, it's ideal. You might have a different conception of entropy. So I still haven't see, now you see why I'm saying it's really hard to understand what entropy is, because it's just this mathematical abstraction. You don't have it like the other 4 physical quantities or the 7 quantities that are fundamental to physics. So this is a derived thing. So now there's a Wikipedia entry, and you can check this, guys. Look up negative temperature. And so when I was taking statistical mechanics and thermodynamics, I'm like, what? I thought you had absolute zero. You can't go below that. How can you have negative temperature? And so I'm just going to read this. It's very informative because I said there are 2 conceptions of temperature.
And we mean negative in the absolute sense. Like when you have something that's 0 degrees Celsius or Fahrenheit, that is not the same as having 0 Kelvin.
Well, this goes below 0 Kelvin.
Right. That's why I'm saying that this is definitely not the same thing as like, oh, it's it's minus 20 Fahrenheit. That is not a negative temperature in this sense. That's a very high positive temperature in that sense.
Yeah. So just look it up because it's very informative, because it like I said, it depends. What we call temperature, there are 2 definitions. Most of the time it'll work, whatever you're talking about. But when you get to certain systems, it's like, normal conceptions of it, traditional conceptions are not rigorous enough. So let me just read this. Temperature is loosely interpreted as the average kinetic energy of the system's particles. And the word loosely is very important, okay?
Mm-hmm.
Loosely is very important. The existence of negative temperature, let alone negative temperature representing hotter systems than positive temperature, would seem paradoxical in this interpretation. The paradox is resolved by considering the more rigorous definition of thermodynamic temperature as a trade-off between internal energy and entropy contained in the system, with coldness the reciprocal of temperature being the more fundamental quantity. And I'm not going to read the rest. The important thing is going back to the Clausius integral. And if we run out of time, it might be just as well merciful because we're getting really deep in the weeds here. So the Clausius integral treats temperature as a fundamental physical quantity. The Boltzmann formulation does not. Temperature can be expressed in terms of omega. Okay, and you'll see this in the negative temperature article. I'm not going to go there because the math gets nasty real fast.
So I want to clarify. This capital W is representing a lowercase omega. Is that accurate? Like when you see this written out in most. Okay.
Yes. But sometimes you will see the uppercase
W.
You know how it is with math. They'll just throw whatever symbol. I like W because then I don't have to use special symbols when I'm typing.
Sal, just get a Greek keyboard. Come on, man.
That's what we have to do.
Get a Greek keyboard, man.
So now this is interesting. We can derive concepts of entropy without the second law. Sometimes the traditional definition of entropy was tied around the second law, but you can define it in statistical mechanics without the second law. I know that may sound heretical. So this is one of the problems. Depending on what body of literature from what era, you'll get a slightly different definitions of the second law and entropy. So again, going back to the Clausius came up with his ideas even before we had notions of atoms. And so just bear that in mind. And then to make matters worse, we started to transition from classical mechanics to quantum mechanics and oh boy. All right, so you're going to get so many threads of different, even in physics today, we use a lot of classical mechanics, even though we formally know it's not exactly right. But it's such a powerful tradition, and it actually works so well for most everyday kind of physics. So much physics is actually based on approximations of classical mechanics.
Right.
You don't really use a lot of quantum mechanics for everyday physics. Chemistry is quantum mechanics, tons of it, but then you kind of abstract the quantum stuff away anyway.
Yeah, it's one of those things where it's like, you could use, I suppose, the standard model to describe your cooling cup of tea on the counter, but my goodness, would that be a pain in the butt? Let's just use some classical equations that take all this into account and approximate it within a margin of error that is smaller than you're ever going to need.
Exactly. So since I don't have my Greek keyboard, I'll say W is the number of microstates independent of second law. Now, the meaning of microstates, I'm going to cover that. It's a nightmare. Okay, guys, just accept it's a nightmare. I'm going to touch on it a little bit. KB is Boltzmann's constant and S is entropy. Now, we have things called natural units, which means just one. It's what we call dimensionless. You can actually have it dimensionless, where then omega is just a count of microstates. The log of omega then is the log of the count. And so it ends up being dimensionless. So what does that...
Here's one point. The reason I don't like people calling moles a unit is because it's technically dimensionless, because it's just a count of how many of whatever the thing is. So it's more like a dozen than it is like an inch.
Right. And so this is where, going back to the 7 fundamental units where we say moles, it's not really a unit, but okay, all right. So I agree with you there. And the nice thing is, I don't think we've had a major disagreement in this discussion so far.
No.
This is nice. So when you ask me what the units in our debate, what's the unit of entropy? I said joules per Kelvin, but technically you can actually make it dimensionless, which is amazing.
Oh, yeah.
Okay?
If you had given an explanation using microstates, I would have also accepted that.
Okay, thank you. So the atomistic formulation of the second law, and I had to cite this because even in my textbook, I didn't hear it this way explicitly. Now, my professor said there's some violations of the second law when you have sparse gases. And if we have time, we can go into it. It's not that big a deal. But so this was what's highlighted in yellow is an exact quote to the best of my knowledge. It says, entropy increases most of the time, but there are exceptions, albeit very rare. So that's one formulation of the second law. Okay.
Yeah. So
all right.
one of the
I've never, yeah.
So one of the things is, and actually this is something that I just had Mr. Batman in my debate with him just flatly deny that entropy can ever go down spontaneously. And so one of the things about quantum mechanics is any given microstate there's odd chance that the system can take it if it's a microstate physically possible for that system. And the thing is, that means that some of the microstates that it can take on, and for now we can just think of microstates as the actual state of every tiny little subatomic particle. For now. It's a little bit more complicated than that, but we'll just think about it that way. So because low entropy microstates are physically possible, there's always a small chance that the system will take that state upon observation, which can then lead to a decrease in entropy. Now, on average, that doesn't tend to be what happens because the majority of microstates in any given system will tend to look about the same when you measure it using classical scale measuring devices. And those are higher in entropy than the ones that will look very, very unlikely, basically. So, for instance, if you have a microstate where you have a really high temperature gradient from one side of a system to the other, that's a relatively low entropy state. And there are only a few microstates, relatively speaking, that have that configuration, where there's huge numbers that have a configuration where temperature is more or less equal across the entire system. And so if you're measuring microstates that can account for the measured macro state, the essentially thermodynamic equilibrium state where everything's the same temperature, has higher entropy. In other words, more of the microstates that the system could be taking to result in this, than the one where there's a high temperature gradient, where one side is really hot, the other one's really cold. There's fewer microstates that can explain that measurement. So it has less entropy.
Well, I totally got lost in that. I'm sorry. I have a simpler example of.
Okay, go ahead, please.
With just two, but that's going to be way later if we get to it. But we're having so much fun. And are we already at 2 hours?
No,
wait.
1 hour.
I'm on Eastern time.
Yep.
Okay, so I might have time to cover it then. Okay. First, there are two ways to define microstates. It's the classical way and then the quantum way. Ironically, the quantum microstate is actually considered easier because you just deal with energy. In classical microstates, you deal with position and momentum.
Mm-hmm.
And okay, so this is what we had to do to kind of understand what classical microstates are. Microstates that involve the position and momentum of every particle. And you get these humongous numbers when you're counting microstates. It's just absurd. So suffice to say, this is a big can of worms if you ask what microstates are. If you go to the Wikipedia entry on microstates, at first it looks not too bad because they talk about coin flips. 2 coins, it could be heads, tails, tails, heads, and tails, tails. You see each of those are microstates. It's like, yeah, that's kind of a nice way to start. But when you actually start trying to do this with position and momentum microstates, it gets nasty fast. And I'm just showing a clip from, we had to study the Liouville theorem on this. It involves Hamiltonian mechanics and stuff I can't even do anymore. Not that I knew how to do Hamiltonians that well anyway. Okay, so going back to this definition by Boltzmann, S equals KB logarithm W. W is a nightmare. Okay, just suffice to say that's a nightmare. All right. It looks easy enough. All the nightmares kind of compartmentalized away for where you don't want to look. Okay. Now I will dump in the chat. Let me see if I have this. I have where you can actually count the microstates for like a monoatomic gas. You enter in some parameters like the temperature, the size of your container, the size of your container, and the number of moles. And it'll actually count them. It'll do the calculation for you.
Well, that's
So
nice.
those who really want who want to just nerd out, I'm going to give you a chance. You can just play with a
So,
spreadsheet.
do you have a moderator role on the channel?
No.
Okay, so just type in anything in chat first, and then I'll make sure that I toss in a moderator role, and
Oh, thank you.
then you'll be able to add those
By the way,
links.
you're a moderator on my channel, so thank you for
Am I?
reciprocating.
Nice.
Yeah. If you're not, I'll make you one.
Okay. So yeah, just type in anything. Also, by the way, guys, Omega's in the chat for Sal. Apparently, that's now a thing. So show your support for Sal coming on here. Put in an Omega, and let's see. There you go.
Okay, so these are the links to Sacred Tetrode. Just the explanation, and then I have links to the. Hang on, those weren't the computational things. Oh, please tell me I didn't.
Uh-oh.
I have to just, if you'll excuse me for just one moment. I'm sorry.
You know what? We'll just do a quick intermission, and I will refill my ice water, and then we'll be back in just a couple minutes or so. So, guys, please stick around. We'll be back very shortly to talk about things like microstates and whatnot. But yes, get those omegas in the chat.
I want to take a moment to talk about something serious. There is a problem facing late surviving non-avian dinosaurs in modern America. Hunting is very strictly regulated, and only allowed at certain times of the year. This means that for much of the year we have to rely on farm-raised food, which means money. If you want to help a starving dinosaur, please consider donating on Patreon, or buying from my merch store. Links are in the description. Please help. Dinosaurs all over YouTube are depending on you to help them through the hunting off-season.
All right, we are back, and before we get right back into it, I just want to say something. So, as I think most people know, I live in the desert, right? And we've been having, it's monsoon season, and we've been having a pretty crazy monsoon season. This has been, I think it's like in the top 10 monsoon seasons in the last like 170 years or something. So, it's pouring out, and so when I got up and took my headphones off, I thought the sink was running. And so I went to go check, and I was like, the sink should not be running right now. So I go to look at it, and no, it's just the water falling from, like, the gutters and whatnot. So it's crazy out here. So let's see, let's take a look at what I missed. So, okay. So at one point, Andrew Cumming had mentioned, and I saw it, that increasing entropy can be thought of as an increasing number of microstates that the system can take, and that's basically the case. Yeah. So entropy is proportional to the number of microstates that a system can take, while resulting in essentially the same macro state that you encounter at classical scales. So that is a way to think about it. Leophilius says this is brilliant and funny. Let me know which exact part you were talking about. I suspect it was my sad, sappy commercial, which is how I start my intermissions. Venerable Bede is now able to use eth, which is, of course, one of the letters that English has lost. I missed 65 million years of evolution, did I? No, I was around for it, kind of. Europe or China, crazy rain or just lot. Actually, it has been crazy here. I've been in a flash flood watch for basically the last 3 weeks. Technically that's not true, but basically we've been in it more often than not for the past 3 weeks or so. It's been just wild. Oh, and Icarus found both W and Omega in the formula. So I guess that W for microstates is just a weird sort of thing. Oh, Leo, I'm glad that you like that one. I think that was some of my better work. Just in terms of being funny. Yeah, I'm a big fan of that one. Sal, any luck?
I'm almost there. Hang on.
Okay. So, Thorn is also a good letter. Yes. Got Robert Madwell pointing out that Thorn is a great letter. I don't know if you know about the letters that English used to have that now it doesn't anymore, Sal.
I didn't know that.
Yeah, English used to have basically 3 letters that it has lost. Win, Thorn, and eth. Now, Win isn't much of a loss because we basically just use Y, so it's not a big deal. But Thorn and eth were used for the th and th sound, like in thigh or thing. That's kind of too bad because TH, I don't like it as much. I do prefer Thorn, which I think the Venerable Bede here agrees with me. Venerable Bede, I was actually interested to see whether or not this crazy monsoon season was closely related to climate change, but I didn't actually see any significant change in like the frequency of heavy monsoon season years over the last 150 or so years. So it seems like it's actually not that tied to climate change. Also, of the places that have been changing temperature, this region hasn't actually been changing temperature nearly as fast as some other places. So the results of climate change here in the Valley of the Sun in Arizona has been relatively mild. Now, granted, that's partly because we've already started out in one of the hottest inhabited areas in the entire planet. So, this is a place where 120 isn't unheard of. Win does represent the sound W, but they're not the same letter, man. You can't tell me that you look at a Anglo-Saxon codex from the 9th century, and that win is just W, because W came from the letter U being doubled up. So, all right, Sal, what do you got for us?
Okay, so if we have anyone interested, they could play with the Sacker Tetrode spreadsheet. I have it in OpenOffice and Excel format. I dumped it in the chat. I will start also, before we close, I'll dump links to some of my talks on thermodynamics that will have the links in the video description too, so you don't have to lift it from the chat. If anyone's at all interested, I have nerd stuff on my channel. I have a lot of nerd stuff. I'm probably the nerdiest creationist in YouTube. So
I consider this to be a good thing because I think if you're trying to do science stuff, you should be nerdy. And I think the fact that some of the other voices in creationism are more interested in MMA than they are in science is to the detriment of their channels. Not that there's anything wrong with MMA.
Well, that just helps me to stand out, which is good for promoting my channel. So,
which, by the way, your channel is linked in the description. So anyone here, if you like hearing what Sal has to say, and you want to hear some of the better YouTube creationist content out there, I would highly suggest linking to that. Subscribing to Sal. So yeah, if you want to hear some of the best that YouTube Young Earth Creationism has to offer, link in the description.
Thank you for the plug. So Frank Lambert. So as I said, and the meaning of W and computing it is a mess. What we normally would do in practice is you have some specialist that's going to do the equation for you, and you could put it in a spreadsheet. Trying to do this from scratch is just miserable. Okay. Calculating entropy with the Clausius integral is easier. So if we had to pick, it's like, okay, we can. This is nice because you could measure it. You just use thermometers and calorimeters.
Mhm.
Doing it the Boltzmann way,
That's a bit of a pain.
yeah. So Frank Lambert said, he is known for his advocacy of changing the definition of thermodynamic entropy as disorder in U.S. general chemistry text to its replacement by viewing entropy as a measure of energy dispersal. So the idea of where this emerged, unfortunately, was by Boltzmann and Gibbs, who were pioneers of thermodynamics. So it was understandable people kept saying disorder because Gibbs and Boltzmann said so.
Yeah.
But it's not actually reflected in the equation. And Frank Lambert said, just stop using that. It's been agony. Because when you actually start calculating, it's like, well, you don't have to describe it in terms of order or disorder. You either describe it in terms of microstates or like this Clausius integral. And it's like, yeah, it's like, is the English word or concept or order or disorder the actual conception? And it's like, so if you want, that's the problem is with length, time, and those other 4 fundamental quantities, you're not going to have a lot of argument. What's the appropriate English or, human language term for it?
Yeah.
But entropy, it's like, is it disorder? So I'm just saying that it's not a good definition, disorder and order. And I'm going to also I have a textbook author who took offense to that. I was pointing out he didn't get it right and he had to defend himself. And it's really kind of funny. Some of you know Larry Moran. He runs a Sandwalk blog. And you can barely see the URL. It's the skepticalzone.com in case you're curious. Skepticalzone.com. Just look up Granville Sewell and you'll be able to find it. But Larry Moran said this, because he's a textbook of biochemistry, and he defined entropy in his textbook, and I confronted him about it, and he said, this is how he responded to me. He said, textbook authors have been discussing this issue for decades. It's like, how do we explain entropy? So that's this issue. Most of us understand that there's a statistical mechanistic definition of entropy, and we understand that the simple metaphor of disorder randomness is not perfect. However, we have all decided that it is not our place to teach thermodynamics in a biochemistry textbook. We have also decided that the simple metaphor will suffice for getting across the basic concepts we want to teach. I've talked about this with Cox and Nelson, the authors of the Lenigert textbook, and with Don and Judy Vogt, the authors of another popular textbook. Sal may not like our decision, but it was a very deliberate decision to dumb down a complex subject that doesn't belong in biochemistry textbooks. It's not because we don't know any better. There are a dozen such issues in my textbooks, cases where difficult terms are deliberately oversimplified. On the other hand, there are some terms in my book that I refuse to simplify, even if other authors did so. And what I said to Larry Moran is, why don't you use Lambert's definition of entropy? And I'll show some examples of this. He said energy dispersal, or the spreading out of energy. Even that's not 100% rigorous, because there's some pathological examples where it's wrong, but in my opinion, it was better. Okay, because the alternative is to do this, and that doesn't really help. Okay, so I'll give an example where entropy there's a special case where thermodynamic entropy does have some measure of organization and disorganization. And this is a special case.
Right.
This is with the mixing of gases. So say we have two monoatomic gases. One is, we call, one species represented by the blue dots and the other by the red dots here. And we could say then it's more organized, so to speak. Okay. And this is where it starts. It's like, well, who's to say what means organized or less organized?
Yeah, those are human judgment calls that nature doesn't care about.
Right, exactly. But let's say, in the metaphorical sense, we can say we've organized this better because we compartmentalize all the blue in one compartment and all the red in the other. And it's separated by this valve that's separating the two containers. When we open the valve, they mix, and we could say it's more disorganized. All right. Again, these are English. These are kind of qualitative terms. These are not, physicists might cringe that you call it more organized or disorganized. I mean, okay, in a quantitative sense, it's like, it's a little hard. But in the chemical sense, let me see if I have an example of this. In the chemical sense, if we go from the closed to the open state, we can actually, using the Sackur-Tetrode equation, say that this state has a higher entropy. So this is the one case you could say, okay, in this special case, the level of organization can be, you can use thermodynamic entropy to state whether one thing's more organized than the other. This is in contrast to the earlier case where we did with mice and men, all right? We could say that the humans, a living human is more organized in one sense than the frozen dead rat. So this is a contrast where, in the case of of mice and men, entropy is not a good measure of organization or order or disorder. In this case, it is. So the point being is it a measure of organization or disorganization? Is it a measure of is entropy a measure of organization or disorganization? And I'll say it depends.
Right.
And that's exactly why you shouldn't use it to make arguments about organization or disorganization, because it depends. You want a more stable definition of organization and disorganization. And so don't use entropy. But at this point, I'm just trying to give some illustrations of entropy. You can actually calculate it. It's kind of nasty. And this is the Sackur-Tetrode equation. You can go through the trouble of typing this in yourself. You have to figure out how to compute internal energy here. U is, let me see if I've explained this. Yeah, here. U is kind of the heat energy. That's colloquial term. It's the proper term's internal energy. And V is the volume of your container. So going here, you can calculate the volume of the container. U is the internal energy. And so that can be calculated using the ideal gas law and some other things. So in my spreadsheet, if you enter the temperature, you'll be able to compute the internal energy. And N is the number of moles. That's all you need, these three parameters, and you can calculate the entropy, the absolute entropy of an ideal monatomic gas. Again, that's an ideal gas. No gas is ideal.
Everyone likes to calculate things for ideal gases, and gases hate being ideal. Very annoying.
Yes. Okay. H here is Planck's constant. So you have you have N in three spots, but that's still the same N. You have V here, and you have U. M, I think that's the mass.
Yeah, it says
that's
mass
the mass
of gas particle.
Right. That's the mass of the gas particle. So then you can calculate it. And like I said, you needed some physicist, mathematician to actually do all the mechanics, because how he came up with this was not easy. They had to use some quantum mechanics too. And this only works for ideal monatomic gases. Try doing like liquids, and you're going to have a nightmare. You might be dead before you figure out how to do it for certain liquids. Okay. everyone likes ideal monatomic gases, and like Dapper Dino said, that they're not any ideal monatomic gases.
But
So
I will say this: in many cases, ideal gas laws do approximate what happens in real life, because at certain scales, many real gases act enough like an ideal gas that it's like you can still kind of use the equation and it'll be okay.
yes. So when I open the valve, this is what they call an isothermal non-adiabatic process. That means we keep the temperature the same, but we are able to do that without adding or subtracting any heat from the system. So those are the conditions for this to hold. And I think what would happen is you calculate the entropy here with this gas, because it has a different mass than this gas. And then you do some mathematical gyrations, and you get the change in entropy based on mixing.
I'm going to make that big for a second.
Yeah.
Oh, that didn't really help. Hold on a second. I'm going to just move. Oh, nope, that's not what I meant to do. Where'd you go?
So I want to contrast this. If you want to, like, say, you want to measure the length of something, you just take a tape measure. Easy. If you want to measure amount of time, you take a stopwatch. You want to take a measure of weight, you can, you measure mass by measuring weight. You just use a scale. To do stuff with entropy, it's a nightmare.
Yeah.
It's just a nightmare. And God bless the people who were working on entropy. It helped us make better steam engines. Okay, so it was important in that concept.
Actually,
in that sense,
I pointed that out on Smoky Saints channel because we got into a little bit on entropy there, and I was like, a lot of this was just we came up with this science because we were trying to make better engines. Because a heat engine. The way a heat engine basically works is the energy gradient that you're drawing from is a hot source and a cold heat sink. And as something flows and gets hot at the hot source and then flows down to the cold to release that temperature, you have to spin something in the middle, right? So a lot of this math was done to basically be like, okay, we want to make a better train engine or something like that. So that way we can be more efficient with our fuel and get farther on the same coal or whatever we're using. And, it seems like it's very, up in the, ivory tower of academia with all these numbers and stuff. But remember, this was all a very practical, it still is a very practical thing. You have to take this into account if you want to make an engine for your car, because you have to know, okay, the fuel I'm assuming has this much chemical energy per unit mass. It has this energy density. It can be released like this. How do we design it so that we have, the maximum efficiency or the optimum efficiency, because it might not be maximum going from here to here. We're going to have this much waste heat. That's part of all this thermodynamic calculation. How do we cool the waste heat? All of this stuff is really important to mechanical engineering in terms of heat engines, which are almost all the engines you're ever going to meet are heat engines.
Exactly. So that's at the macro scale. What happened is when, in the time of Boltzmann and Gibbs and Maxwell, they began to consider, this is when they were proposing atomic theory, which was very bold at that time, because the idea of atoms was like heretical, right? And so they proposed the idea of atoms, and they said, let's try to extend the ideas of entropy down to the atomic scale. And that helped with our understanding of chemistry, because then we could use calorimeters and thermometers to help understand what's happening at the molecular scale. So this is kind of the development of the thought over time, and then the math just got nastier and nastier. But it does help now in the modern day, help us to understand chemical structure. So you can understand why biologists and protein biologists would be interested in the concepts of entropy. And even I, even though I work in structural biology and protein biology, I haven't had yet to do any entropy calculations to calculate protein structure, thankfully.
Yeah, I was going to say, I'm sure you're really upset about the lack of entropy calculations that you've had to do.
Yeah. I haven't had to. There are biophysicists that's all they do. This is very, very hard stuff. And like I said, you want to measure temperature, get your thermometer. You want to measure length, just tape measure. Trying to measure entropy, it's just a nightmare. And so again, echoing my professor's statement, I don't understand entropy. That's what he meant figuratively speaking, because it's a mathematical abstraction. And so I have some examples here, but I think everyone, especially you, Dapper, understand what's going on. I'm not going to belabor some of these points. There's ideas like what they call multiplicity, and this is from a slideshow I did earlier, and it's not important. I'm just saying this is a minefield for ID proponents and creationists. This is just a minefield. Don't go there to try to argue for God's creation with this stuff. That's why I'm here. I'm trying to. It's rewarding to try to teach science, because I like teaching science, because I like studying it. And I like to help my fellow creationists understand when they're making bad arguments.
Yeah.
So I can give them what I think are better arguments.
Well, one thing I would like to say is, guys, if you have questions, start getting them in, because I think we're probably going to start winding down in not too long.
Yep.
So if you have big questions, please. And also, I like the heads thing for microstates.
Yes, this is a low multiplicity. This only has one microstate. Whereas if you had, it's kind of a nasty thing, but there are many ways to configure this number of coins where it's 50% heads, or roughly 50% heads.
Right.
Many microstates. There's only one microstate that corresponds to the macrostate of all heads.
I also, I know a fair bit of my audience are people who do a lot of tabletop gaming. So another way you could think about it is like this. Most people here have rolled more than one 6-sided die at a time, right? So if you take 2 6-sided dice, by far the most likely roll is 7. There are a lot of ways to roll a 7 on 2 6-sided dice. But 12 and 2 are much less likely. There's only one way to roll a 2 and only one way to roll a 12. And you can measure, it's normally distributed, the different rolls that you can make, how likely they are. So in terms of entropy, you can think of 7 as being a high entropy roll, and 2 and 12 as being extremely low entropy rolls.
Low entropy.
And the more dice you add into
good.
this,
Perfect.
the more dice you add in. So, if you've ever played Dungeons & Dragons, sometimes you're rolling 5d6, right? Well, okay, so the average roll there is, 3.5 times. So, like, about 18? It's 17 or 18. They're about equal. But that's a very, very likely roll. Whereas the roll of 30 or the roll of 5 are also very extremely unlikely. And the more dice you get into it, the more you can see how there's so many microstates that the dice could take. So, for instance, if you've ever played a tabletop war game like Warhammer or something, where you're throwing 40 d6 out there, well, now you don't add them up in that game, but you can see what I mean. So when we're talking about atoms that can have, trillions and upon billions of atoms in a very relatively small, system, and each one of them has not just heads or tails, but has a whole host of options for momentum and position that they could take. You can see why trying to calculate microstates for a system by just literally counting them becomes prohibitively complicated.
I mean, I was giving, with the Sacro-Tetrode equation, you'll just get insanely large numbers where it's this number raised to this power, and then you take that and raise it to, you just get these absurd numbers. I mean,
when you had to start raising your power to another power, you're oof.
Yeah. For like the ice cube example, there are more possible microstates than there are atoms in the universe. You just get these insanely large numbers. It's just absurd, and you can play around with it with the Sacro-Tetrode equation. You could probably put in numbers that's just going to blow my spreadsheet apart, because
you
can't handle it.
Actually, one thing that I like about the dice analogy is, while you can see why 2 and 12 are low entropy, you can also see that sometimes you do spontaneously get them. It is possible to go down in entropy spontaneously. Yeah. Now, if you're rolling 10,000 dice, will you get all ones? Well, you could. Nothing prevents it. It's just vanishingly unlikely.
Okay, so I said I had an easier example of spontaneous organization. If you had only one blue molecule and one red molecule, there could be a time where they spontaneously separate back into the blue on the left side and the red on the right. See, it doesn't stay mixed. That's why I was saying sparse gases, that's the exception. That's where, you can, that's one simple example. That's the one that my professor gave me, to just deal with sparse gases, one or two molecules in the system. It's very hard to describe what's going on anyway. So, that's the example where you can get spontaneous organization.
Awesome.
So
now we have some nice analogies for entropy. Coins and dice.
Yeah. So now this is where I started going to protein chemistry. This is from another one, but I did have a quote here. This is from the one creationist. There are only 3 creationists I know that get this right, me being one of them.
Ouch. Creationists, get on the ball, man, with the entropy thing. Stop being silly about entropy.
So one of them is Robert Gaines. He's a physicist, okay? And that's why it's like applause to him. He actually knew Nobel Prize winner Eugene Wigner, Nobel Prize in Physics. And so here's an example. He said, we noted earlier that entropy, and this is, you can go to the links there that I provided. The book is Origins and Destiny. It's available for free online. He said, we noted earlier that entropy can be correlated but not identified with disorder. Okay, so what is correlation? You can correlate reading ability with shoe size.
You can.
Okay, so like the bigger their shoe size, on average, the reading ability is probably better because just they're older and they're farther along in school. So you can correlate shoe size with reading ability, but it doesn't mean shoe size is the same thing as reading ability, okay?
Right. Getting your kids' feet enlarged, if that were possible, isn't going to help them read better.
Exactly. So we noted earlier that entropy can be correlated, but not identified with disorder. And we said, moreover, that this correlation is valid in only 3 cases: ideal gases, isotope mixtures, and crystals near 0 degrees Kelvin.
One of which doesn't even exist, by the way.
Yeah.
So, and the other 2 are not the kind of thing you're measuring for most biology stuff.
Right. The truth of the matter is illustrated by considering the 2 chemically inert gases, helium and argon. In our mind's eye, we imagine 2 balloons, one filled with helium and the other with argon. First, we lower the temperature of both balloons to 0 degrees Kelvin. This makes all the gas molecules stop moving in either balloon. Next, we get the molecules moving by heating both balloons to 300 degrees Kelvin, room temperature. Were we to mathematically calculate the increase in entropy, we would find that it was 20% higher in the argon balloon than in the helium balloon. 154 versus 127 joules per mole per degree Kelvin. But since helium molecules are 10 times lighter than argon molecules, they are moving 3 times faster and thus are more disordered. Here then is an example where higher entropy is accompanied by lower disorder, thereby demonstrating that we cannot identify one with the other. In the particular example cited, the greater argon entropy comes from the closer quantum translational energy levels identified with its greater molecular mass, as described by the Sackur-Tetrode equation. Okay, so one creationist gets it absolutely right. And then there's the Sackur-Tetrode equation again, and we covered that.
I'm not seeing it come up, Sal. Oh, I just now saw it changed. Changing configuration.
Okay, I was just a little quick. And this again was derived from another. This is slides from another presentation, but there was something I wanted to share here. There was one of Intelligent Design's founding fathers. This is the book that basically started the modern intelligent design movement, 1984's Mystery of Life's Origin. Here they actually do use thermodynamics, and they use this concept of configurational entropy. And that's a little bit easier term. It's kind of like the two gases, like if you compartmentalize substances, in one container and the other, that's a form of configurational entropy, where you're just, configuration or compartmentalization. That's not exact, okay? But I'm just brushing through this. This is the one time it was also treated correctly, but it was a million times harder than it needed to be, because you could just disregard it altogether and not even use the term, and you'd still get the same result, but it's clearer.
We have a question from Robert Madwell, and I don't know the answer to this. You might, though. Who came up with the creationist argument from the second law of thermodynamics? So do you know who was the first person to use this? Because I'm not sure.
It's widely attributed to the Institute of Creation Research and Duane Gish.
Okay. I mean, he's one of the first young Earth creationist speakers that ever existed. So yeah, that makes sense.
Yeah. And that's unfortunate because he's a chemist and he should have known better. Goodness.
Well,
but it probably wasn't his specialty in chemistry.
I've read his books, and I'm not terribly surprised that he got that one wrong.
Yeah.
There's a lot.
God rest your soul, Professor Gish, but you got that one wrong. Sorry.
You got a lot of stuff wrong, Sal. Let's be honest.
Yes, let's be honest. And see, this is where I get a lot of flack. It's like, Sal, you're not helping our side. I'm just like, I think I am. Why don't we get it right?
Look, if creationism is
if
true,
I were Duane Gish, I'd be grateful for Salvador Cordova trying to say that wasn't right.
If creationism is true, then there should be no problem with getting the facts right. And if there is a problem with getting the facts right, that's a problem for creationism that they need to deal with in-house.
Yeah, exactly. So this has been a great discussion, because I think I've given mainstream science, and I hope creationists will actually improve their arguments by not using these second law arguments.
If I could finally say that I've, for the last time ever, heard the second law of thermodynamics as an argument against abiogenesis or evolution, anything like that, I will be a much happier person, because it is annoying.
Before we close, so I'm going to highlight this term, this configurational entropy here. This SE, if you can separate out the thermal and configurational parts. Now, most physicists really cringe at that, but materials scientists do the separation. Just saying, okay? The engineers like doing stuff like this, the physicists cringe, okay? So you won't actually see this separation in physics books. You will see it in materials science books. And I'll show a little bit of what this term means. Going back to the Sackur-Tetrode equation. It's actually just like the change in you see how the volume change here? It's a small volume. Sorry. In this case, and then when you open the valve, it's a larger volume. So you can actually change the configurational entropy is kind of changes in position. So configuration is positional changes, not changes in the kinetic energy, the internal energy of the system. So how does this relate to abiogenesis? James Tour did a lot talking about the purification of substances. I'm just going to show a picture here, just pictorially. This would be kind of like high configurational entropy, because you have mix of different kinds of coins. If you segregated them out, you would say, kind of, again, in a conceptual sense, that if you put all the pennies together, the copper coins together, and then the whatever kind of metal coins together, compartmentalize them out, you are reducing the configurational entropy. But you don't have to say that. You don't have to even use the word entropy. It's just like you purify the substance, and you can just leave it at that. You don't have to use the word entropy. But the early intelligent design books, even though they treated the topic correct, versus the way Duane Gish treated it. So these are ID proponents. They're old Earth creationists. They made it way harder. Walter Bradley, I'm pretty sure, was the one who wrote this part. He had two other co-authors. He didn't need to go here. Oh, by the way, you're talking about omegas instead of W. That's the capital omega there. So see, I was just saying some people will use the capital omega.
So, Sal, I do want to point out, I did put in the internal chat a link from Nestle 20 from Sharon Glotzer, who is giving a talk, and let's see. So she's reporting on a crystal, or a quasi-crystal, and I'm summarizing a bit here, that apparently, as she increases the entropy in the system, it produces highly complex ordered structures. So that is an interesting little bit there. So I will put actually that link in the chat too, in case anyone
Thank you, Nestle.
Yeah, in case anyone wants
to take a look at that. Anytime he speaks, I'm always very impressed. He's very knowledgeable.
Well, Sal, it sounds like we're probably ready to basically wrap it up. So if we have any last questions come in, we can take a look at that. But we've been going for, a bit over an hour 40, so I think it's about time we can start wrapping up.
Yeah, I'm getting. This has been a great talk, and if you could permit me, I'd like while we're taking questions, it would mean something to me if I could drop links in the side chat for.
Oh, absolutely.
For some of, if you want to hear where I both criticize ID and the use of thermodynamics, but then also you'll hear my arguments in favor of ID. It's in these links.
Okay. Well, absolutely. Feel free. And actually, if you want, you can email them to me or something, and I can add them to the description. So that way,
okay,
you can just check the description after, if you're watching this in the future. First, hello from the past. And if you are in the future, please check the links in the description, and there should be some links there for you, in addition to Sal's channel. So I'm not seeing any more questions directly, so I will give a little bit of what's coming up. So as you guys know, Tuesday we're going to have Kent with Bent. I'm hoping to have Maddie from Science Side Up back on. For that, let's see. Thursday should be Canadian Young Earth Creationist episode 4. Then Saturday should be another stream about spirit science. I don't know if I'm going to have a guest. It's sort of just one of those things where it's like, sometimes people come by. So then the next Tuesday, let me look at my calendar here. So then the next Tuesday is the 3rd. There should be another Kent with Bent. Then Friday, I think I'm actually going to be mirroring the video that I did for Vice Rhino on the channel that day. So feel free to stop in for that if you haven't seen it, or even if you have and you liked it or didn't like it, I don't know, whatever, just watch it. So that's on the 5th. Then Saturday, the 7th, is going to be a Leaving Young Earth Creationism with Kat. So that is the plan there for the next couple weeks. And Sal, looks like you got your links in there.
Yep, and I will send you my links, my set of links. And I've been really looking forward to the show for a long time.
Me too.
This discussion went really well with you there, and because you were able to give me feedback if what I said made sense. And it was a very comfortable conversation.
Well, yeah, I'm an easy enough guy to get along with. Just don't be directly dishonest to me. That's one of the few things that I ask of people. And don't be mean is another one that I like to ask of people. And you so far, you've managed to not run afoul of those very easy to follow guidelines for interacting pleasantly with me. Yeah. So I do want to say thank you. Is there anything coming up on your channel that you'd like to announce for people who might want to go check that out?
Yes. I'm trying to get back to business because there was a big flap in my church recently. It's in the Washington Post, McLean Bible Church. I'm their lawsuits. There were armed police officers in the middle of our worship service, hauling someone out this last Sunday. A lot of drama, but I'm doing less of that, and I'm trying to do this coming Tuesday. Tuesday evening, about 7:30 p.m. Eastern time. We haven't finalized the time. A geospatial engineer will be sharing how she teaches the Christian faith and a little bit of creationism and intelligent design to her teenage daughter who's going to a secular school. And so this should be this should be interesting because she and I are of the mind that secular studies are very important. And hopefully I've tried to show that in what I've taught today. Hopefully you could see that I've taken my secular studies very seriously. And she has kind of the same mindset. So on my channel this coming Tuesday. Beyond that, I don't know what's going to play out.
All right. Well,
it's usually last minute.
I get that. So like I said, guys, please do go ahead and check out Sal's channel. It is linked in the description. I'm there. I can't say I'm there for every stream, but I'm there pretty frequently. I like to at least drop in and say hi and see what's going on. Sometimes I stay for a lot longer. But so yeah, it's a place that I will go because, well, quite frankly, it's one of the few Young Earth Creationist channels that isn't just full of vitriol all the time. So that's why I go there, because I just because someone is my I guess I could say intellectual opponent, right? Like Sal and I have some disagreements that we've discussed, and that we have some really big disagreements, but we don't let it become something that causes us to mistreat the other person. And I think that is a valuable skill that is rare on the internet, is to be able to disagree without it becoming just incivil, right? Just be nice to each other, be kind to each other. The fact that you disagree doesn't make that person any less of a person who's valuable, who's their own moral agent. If you're going to take, like the Christian line, or for that matter, the general Abrahamic line, who's made in the image of God, if that's something that you believe, that's still true of the other person. So, don't dehumanize your opponents, basically. Now, if your opponent is doing horrible things, like, say, the guy who runs Dinosaur Adventureland, then maybe you can be a bit meaner because, he's an actual charlatan scammer who's selling poison and letting little kids die. So I got less sympathy there, but assuming that's not happening.
Well, at some point you start to feel you have a moral obligation to call something out.
Yeah.
And I was not at that point until I read the stuff this last week about his third wife that he dissed. I'm just like, dude, I got to call this out. I can't be neutral anymore.
Well,
this is, besides, you guys, you want first-rate creationism? Come to my channel. Don't go to Dinosaur Adventureland.
Not only, so here's another thing. To go to Sal's channel, you don't have to sign a waiver saying that you enter Sal's channel at your own risk.
Oh, that is so mean.
Hey, you have to sign a waiver to get onto DAL. So.
Whoa. Oh, I didn't know that.
Yeah.
Oh, goodness.
Yeah. Actually, the Venerable Bead says that there's
to my creationist friends who are watching me, I know you might flip a lid with what I just said, but
get better thermodynamics.
That's just me. There comes a point my conscience would bother me if I didn't say something.
Yeah.
And I crossed that point last week.
Yeah, look, it's the same thing on, say like the I guess the mainstream science side. If there were some person out there advocating for, mainstream conventional science who also turned out to be a weird cult leader who was selling poison, I'd call that out in a heartbeat. This is not a creation versus evolution thing. This is a basic human decency. Don't be an abusive cult leader is a pretty simple rule. There you go. But anyway, I think with that, we're going to start wrapping, or we are going to wrap this up because I told you guys what's coming up. Sal did what's coming up for you. I want to say a special thank you to Danish Debater and Vandalia 1998 for helping support the channel directly via Super Chat. It's always appreciated because, like I've said before, it's ads mean almost nothing on YouTube, and the ability for this channel to keep going with 2 to 3 videos a week for over a year now has been entirely dependent on support from my viewers, whether it be through Super Chats, channel memberships, or donating on Patreon, all of which, you can find linked in the description. Like I said, there's a merch store. Feel free if you want to. So yeah, that is really what makes this possible, because, well, quite frankly, I've cut back on other money-making things in order to dedicate more time to this. And in order for that to be sustainable, I either have to have that support, or I have to cut back on how much time I spend on the channel. And I really feel like this channel is something I want to do and make it be something that I can really put all of my heart into, because I really care about these discussions, I care about these topics. So your support really means a lot. And with that, I'm going to go ahead and put on the end credits, and I will see you guys, hopefully, on Tuesday. I just want to take a second to thank my channel members and patrons, especially those pledging $20 and above. Bob Knob, Benthoven, Ian Chen, Chris Love, Sphincter of Doom, The Venerable Bede, Patrick Dennis, and Res Instance. My channel members and patrons help make this channel possible, and without their support, this channel really wouldn't exist. If you would like to help support the channel as a member or patron, there are links in the description to both join the channel as well as join the Patreon. Patrons and members get mentioned in these credit scenes, as well as getting early access to my scripted videos, and if you pledge $10 or above, you can also get access to various 3D assets that I create for Blender, both for use in the channel, as well as just general giveaways to my supporters to help in any Blender projects they might have. If a monthly or annual pledge isn't for you, then there is also a merch store linked to the description, and if none of that's right for you, please just like and subscribe, because every like and subscription really helps the video out. Thank you.